So today we're honored to have Andrea Lincoln. She recently graduated from MIT and she's currently a postdoc at Berkeley. Andrea is one of the founders and experts of the field of fine-grained complexity. But today she's going to talk about her another breakthrough result where she solved, where she gave surprisingly fast algorithm for the most fundamental algorithmic problem, k-CNF satisfiability. Andrea?
Thank you so much, Sasha. Yeah, so today I'm going to tell you about a faster algorithm for random Kcnfsat. This is joint work with myself and Andrea. So what is Kcnfsat? It's the problem of conjunctive normal form satisfiability with clauses of size k. So let's, be specific about what we mean here. We're going to have n variables, which are, Boolean variables. They can either be 0 or 1. And we're going to have literals. So for every variable, say xi, you can either have the variable appear negated or non-negated, and we're going to call that a literal. And clauses are going to be formed by taking k literals and ORing them together. And formulas are going to be formed by taking m clauses and anding them together. And the question is going to be, is there any setting of these n variables out of all the 2 to the n settings? Is there any setting that causes this formula to be satisfied, to return true? So that's the problem of k conjunctive normal form satisfiability. And as Sasha mentioned, that's like one of the most fundamental questions in at least, sort of complexity in theoretical computer science is how fast you can solve this problem. And the reason that this is so fundamental is in part because this problem is, sort of the central NP-complete problem. So as you might expect, as a result, there's been a long study of how fast you can solve this problem. And, unfortunately for all of us, it'd be nice if there were really fast algorithms, but the improvements have been substantial, but all getting slight improvements in the constant and the exponential. So notably, for large k, all of these have the structure of 2 to the n times 1 minus some constant over k. I put the omega here because while none of these results are able to prove anything better than some constant over k, some of these algorithms might actually run faster than that. Simply, we can't prove that they do. Sort of exciting complication there. However, as you'll see on the right-hand column, these do actually represent improvements in the speed of the algorithms. They get faster as you move forward in time in terms of the constant for specifically k equals 3, for example. So yeah, I want you to sort of take away 2 things. One is it's not really clear how we can do better than some constant over k. And also, people are still making improvements and, trying to figure out how to get faster algorithms for this problem. Finally, you'll notice that there's this strange star floating around next to the big O's, and that's suppressing all polynomial runtimes. So this is suppressing, n squared, n cubed, like you're not going to see those factors showing up because we're fundamentally worrying about exponentials here. Great. So what is random Kcnfsat? So first of all, as might be slightly confusing, this is actually the sort of most studied average case distribution on Kcnfsat. The random here doesn't refer to a random algorithm, but instead a random input distribution. So, first let's describe that distribution, and then let's talk a little bit about average case algorithms and analysis over them. So we take all of our clauses, which are formed by k literals, by just uniformly at random picking each literal from all 2 to the n literals. So this is just sort of the most naive thing you can do. And you form phi by picking a number of clauses equal to whatever you draw from the Poisson distribution centered at m, independently at random across all the, just sampling from this distribution of random clauses. In this talk, I'm going to ignore this Poisson distribution of m. It turns out for the purposes of our algorithms, there's sort of enough concentration of this value that it doesn't matter. And it's a lot cleaner and easier to talk about if we just talk about m as being fixed. We're going to talk about m as being fixed, but I highlight this just because that's not technically the distribution we're operating under. It just turns out it basically doesn't matter for this particular distribution and our particular algorithm. So great, we've got these clauses, and what I want to highlight here in this example is, especially in the second clause, you'll notice that the same variable got picked twice, though, you know, in this case with different literals got picked. And this is totally allowed. Like, it really is IID. We're not doing anything to sort of handle or smooth the clauses. You're unlikely to get silly clauses like this where you pick the same variable twice, but we're not doing any kind of filtering. We're just picking things uniformly. And what I want to highlight about average case algorithms generically is that now that you have a random distribution of your inputs, people talk about, you can't usefully talk about succeeding with probability 1 across all inputs. If you did, you're just back to the worst case. So we're going to be talking about succeeding with some probability in our algorithms. And here we're going to just simply count both the randomness over our input and the random coins run in the algorithm. So this is, to some extent, to simplify statements, but just note that, like, we're definitely going to, in the future when we're talking about our algorithm, it's definitely going to fail on some inputs. And the reason it's going to fail is because if it didn't, we would have a better worst case algorithm. So we're like accepting that things that are sort of far from sort of normal in this distribution, we're not going to handle well. And the goal is to just handle things that are sort of centrally in this distribution well. Great. So now I'm going to tell you about my favorite structural property of Kcnfsat, which is that it has this thresholding behavior. So let me explain a little bit about this, and then I'll sort of explain this questionable picture. So here's the question, like, where do the hard instances of random Kcnfsat live? Like, we know that there are some hard instances of Kcnfsat, or at least instances we don't really know where to solve, like how to solve them quickly. And you might ask, like, okay, well, maybe it's at, like, root n clauses or something. And it turns out that that's probably not true, because when you sample a random formula of length root n, it just looks, it's with such absurdly high probability going to be satisfiable. And you can think of this as being like under constrained in the sense that, you have a certain number of equations roughly in the form of these clauses that you need to satisfy, and we're not constraining the space enough to get anywhere close to being unsatisfied. And similarly, you can imagine, like, okay, maybe it'll be a really high end, right? Like, there's something like n to the k-ish, well, 2n to the k possible clauses. Maybe it'll be somewhere around there that we sample a lot of these. And it turns out similarly, like, no, if you're sampling that many, you're so over constrained, you're like with absurdly high probability going to be unsatisfiable. And you might imagine, like, okay, how does this shape sort of transfer between these, right? Is there some sort of smooth situation? And the answer is no. Within a very narrow range, you move from being with high probability satisfiable to with high probability unsatisfiable. And as a result, this has led to the folklore, claim, or belief that some people will make that the hard instances of SAT should sort of live somewhere around this threshold. So it turns out, like, this threshold doesn't just sort of look like it exists when you plot points. It's also been proven to exist for large enough k, where, like, within a really tiny change, you move from with high probability to with high probability SAT to with high probability unsat. And this is the result of Dingsley and Son's work in 2015. So, our goal is going to be to find a fast algorithm at this threshold, and as a result everywhere, but we're going to talk about the threshold because that's sort of where, for various reasons, it is actually hardest to get these fast algorithms. Notably, outside of it, you can just, to a first approximation, return yes or return no, right? So great.
Andrea, do we know, so we don't know whether there exists threshold for k=3 for 3SAT?
No, I don't think so. So for k=3, I think it's like still open. I think it's not that contentious. Like I think everyone believes that it exists. Yeah, I'll move to the next slide and I'll talk about k equals 3 in the context of this. So the definition of a threshold in this case is that we'd like it to be the case that you have some constant in front of k, sorry, some constant in terms of k in front of n, such that here dk minus epsilon, or dk minus delta, let's say, just to not use the same term again. So dk minus delta for any constant delta, that's going to be satisfied with high probability, and dk plus delta is going to be unsatisfied with high probability. So you want you'd like it to be the case that there's some range where you move between sat and unsat across a space of 2 delta for some arbitrarily small constant delta. Over the space of 2 times delta n clauses over an arbitrarily small delta. And I think in the case of 3-sat, it's still open whether or not this is true. I think we have like a pretty narrow range over which it might conceivably, over which like this sort of central constant might exist. And I believe it's believed to exist, but I think it's not, whatever, the space of things that are probably true but not yet proven. I think the 3-sat threshold exists in those. For generic k, the space that this constant exists is roughly 2 to the k times the natural log of 2. There's also this like constant term in terms of 1/2 and 1 and the natural log of 2, but as k grows, like this term matters less and less. And this epsilon k here is some term that it grows slower than a constant in terms of k. So think it's like 1 over log k is like the size of that term. So these second 2 terms are not as important as the first. And the thing to note there is that like 2 to the k times the natural log of 2 times n, that's roughly the number of clauses that we're going to be thinking about as being at the threshold. So now that we've like talked a little bit about, this average case of random Kcnfsat, talked about the fact that it has this thresholding behavior. Now let's talk a little bit about faster algorithms for random Kcnfsat. So first, all the worst case algorithms, of course, you can run them on average case problems and you get the same running time if you sort of just copy their analysis. Additionally, there are 2 algorithms, both one by Valiant and another by Vyas-Williams in 2019, where they get something like 2 to the n times 1 minus log k over k. Vyas and Williams get their algorithm by reanalyzing PPZ with some knowledge about what exactly is happening at this random threshold. So sort of, working on this analysis side of it. And Valiant's approach is instead sort of a fresh algorithm. Either way, it's really exciting that you see this log k over k because we're very far from figuring out how to do this in the worst case. There in fact exists a hypothesis, not necessarily a very strongly believed one, but there exists a hypothesis that has stood for 10 years at this point or something, anyway, quite a while, that you can't in fact do any better than some constant over k. Like I said, it's not a very believed hypothesis, but it does seem like there's some real difficulty in the worst case of sort of moving beyond this constant over k framing. And we know how to do that in the random case. So our work is going to move beyond this log k over k. And we're going to do this by taking some of the ideas coming from the Schöning and Dantsin algorithm, and then changing the algorithm and improving it by using some nice facts about the random distribution. So in order to do that, I'm first going to explain the Schöning-Dantsin algorithm. Here I put a slash between them because I take some parts of Schöning's algorithm and some parts of Dantsin's algorithm. The Dantsin et al. Work roughly de-randomizes the Schöning algorithm, but I think that some parts of Schöning are easier to understand and some parts of Dantsin et al. Are easier to understand. And so I present this merged representation. This merged representation isn't original to me. This comes from a class taught by Williams and Vasilevska-Williams. Regardless, let's talk a little bit about how this algorithm works. So their algorithm is a local search algorithm. So the idea is they're going to randomly sample some points, where the point is going to be an assignment, of 0, 1 to the n, to all the variables in our satisfying formula. And then you're going to search locally around that assignment for a satisfying assignment. So in the Hamming ball, at distance d from this assignment v, we want to see if there's a satisfying assignment there. And a question you might ask is like, how is this potentially faster than exhaustive search, right? If I sample a random point and then exhaustively search the Hamming ball, we should find a satisfying assignment with probability size of the Hamming ball, and then we took size of the Hamming ball time. So this should also take 2 to the n time. And the answer is they have a faster way to locally search around this assignment v. And I'll describe this algorithm, and then I'll give a picture to give sort of a treatment of that. So I'm now going to start talking about, I'm going to start talking about the Hamming distance, not just as d, but as alpha n. And the reason is, as you might expect, in the end, the Hamming distance we consider is something of size alpha n. It's going to be some constant in terms of k times n. And so just to start talking about things in terms of that size, I'm going to start using alpha n as this Hamming distance. So what's the code for quickly searching locally around an assignment? Given a phi, given a potentially random, potentially not assignment v, and a distance d, we want to deterministically find a satisfying assignment if one exists at distance d. So first, if I is just satisfied on v, then return v. We've found our satisfying assignment. If I is not satisfied and the distance is 0, then return false. We know that we've failed in this path of our algorithm. And otherwise, we want for each variable in the first clause in lexicographic order of phi that's falsified. So there's going to be k literals falsified there, and there's k associated variables. We want to flip that variable to make a new v prime. And the solution is going to be then calling for all of these different flips we made, phi on v prime of d minus 1. And the crucial thing I want to mention here is just that if you start this algorithm by calling phi, your randomly picked up value v, and d being alpha n, by the end of this, we should find a satisfying assignment if one actually existed at distance alpha n. And why? Because at least one of our branching threads should make progress towards a satisfying assignment. So what do I mean by this? I mean, we know, if we have a set of clauses here and 2 of them are falsified, and we're going to pick the first clause in lexicographic order arbitrarily, as previously mentioned. But we know that both of these variables can't possibly, in the sort of true setting of, in any satisfying setting, it can't be the case that both of these variables are set the way they are. All k of the variables can't be set the way they are. It needs to be the case that one of them is set wrong, at least, because otherwise this clause would be falsified. So we get to know that one of these paths of flipping our variable must have been correct and making progress towards a satisfying assignment. And in this silly example where our distance is 2 and k is 2, in order to have a pretty picture, our first choice turned out to not actually make progress towards a satisfying assignment. But by taking the second choice the first time and the first choice the second time, we did successfully find a satisfying assignment. And as mentioned, if there's any satisfying assignment within distance alpha n, this should successfully find it by making progress at least somewhere in each level of this tree. But how many levels of the tree did we, how much work did we spend in order to do this? Well, there's some polynomial time of, running through your m, and, we're running through your m clauses and checking whether or not your formula is satisfied. But once again, we're suppressing these polynomial factors. So what's the sort of exponential time we need to be worried about? And the answer is k to the alpha n, because we branch k times, and the height of the tree is alpha n. So now, why would this run more quickly than brute force? Well, if you're locally, searching at distance alpha n, you need something like 2 to the n over n choose alpha n samples. So this is 2 to the n over, which is the total size of all assignments, over the size of the Hamming ball of distance alpha n from your satisfying assignment. Next, you need to locally, this local search is going to run deterministically in time k to the alpha n. And so in total, their whole algorithm requires 2 to the n over n choose alpha n times k to the alpha n time. And now, when is this going to be faster than brute force, right? We can always solve it in 2 to the n time. So first we can do a simplification of n choose alpha n via this upper bound, which says that n choose alpha n is at most 1 over alpha to the alpha n. Negate this because it was a divisor. And then we can restate everything base 2. And now really what we want is these second two terms. We'd like them to multiply to something that's equal to negative n divided by k times some constant. And I claim if alpha is roughly 1 over k, these terms in fact do equal something like negative n over k times some constant. And if you want to think about this intuitively, this term out front of alpha is going to be the same either way, but log 1 over alpha is going to be larger whenever alpha is significantly smaller than 1 over k. So think 1 over 2k, for example. So if alpha is 1 over 2k, we actually get exactly what we desired. And we get this, faster algorithm, which achieves the bound we'd like. And now the question is, how can we do better, right? So this Hamming ball search was quite expensive, right? We're running k to the alpha n time to search this Hamming ball. We'd like to avoid that. So we're now going to have a picture here where this large gray box is representing all 2 to the n possible assignments, and this green dot is representing the satisfying assignment. So I'd like to highlight that this is a bit of a misleading picture. Our actual space is a n-dimensional space where values are either 0 or 1. And here I'm representing that instead as a 2-dimensional picture. A lot of the intuitions carry over, but just to be clear, this is a misleading picture by being 2D, but I can't draw in n dimensions. So, all right, given that we're in 2D, what does this sort of look like? Well, this looks like us sampling a random point, here pictured in pink, and then searching the Hamming ball, here pictured in purple. So we're making a bunch of these calls, we're searching these random spaces around each of these points, and we're finding that we've searched a huge amount of the space before we get lucky and find a point that happens to actually be within distance alpha n of our satisfying assignment. So it'd be really nice if we could, instead of doing searches around all of our pink points, we could just do it around the point that happened to be very close to the satisfying assignment. The problem, of course, is that this question of an assignment being close to satisfy the satisfying assignment, to be low Hamming distance from a satisfying assignment, isn't something we can directly measure, right? Because we don't know what the satisfying assignment is until we found it. So we'd ideally like something like this. And clearly the amount of work we do would be significantly decreased. But it turns out this is sort of too much to ask. And as an intuition for why this is too much to ask, consider the fact that if we could do this for any Hamming distance, we could take any arbitrary point and ask whether or not there's a satisfying assignment in distance n from it, and just solve satisfiability right there. And our goal is to have some tests that's like not running at exponential time, right? Clearly, an exhaustive search or this k to the alpha n search is enough to check whether or not there's a satisfying assignment, but our whole goal was to not do that search. So we want some polynomial, quick and dirty test that's going to do a pretty good job of telling us which assignments are actually close to the satisfying assignment. So with this weaker ask, we'd want something like this, where we have some sort of gradient, or score for all our points. And some points, of course, are going to be false positives or false negatives on this test. But we want some quick and dirty test that gives us an approximation of whether or not something sort of looks like a small Hamming distance assignment. And setting up this entire framing, we then only need to search over points that sort of look good enough. And of course, this will allow us to search a smaller total amount of space. So how do we sort of phrase this in terms of a setup? Our question for the talk is, what's the fastest algorithm at the threshold? And we're going to define this sample and test algorithm, where you randomly sample points, and then you check whether or not these points pass some easy, polynomial time test. And you only search around that point for the satisfying assignment if you pass this test. So we don't do the whole Hamming ball search. We don't actually verify that a SAT assignment is close unless we look like a satisfying assignment. So, what test should we use? Well, the sort of most naive, silliest test would just be taking an assignment, plugging it into phi, our formula, and asking how many clauses we satisfy. And it turns out that test is the right one. I'll talk about that a bit later, but for a certain class of tests, you actually just can't do better. So, all right, we're going to sample a point V, and we're going to check whether or not it satisfies at least T clauses, and then we're going to run local search around that assignment. And if you want to have a specific number in mind, our threshold T is this particularly heinous equation. You definitely don't need to think about this heinous equation if you don't want to. The crucial thing to note here is that a totally random assignment on a random formula should satisfy 1 minus 1 over 2 to the k times m clauses. And this is close to that, but is a higher. So it's a higher threshold than a random assignment. That's, you'd sort of just think about it that way and not worry too much about these numbers. So let's talk a little bit about the intuition of why this should work at all. Why should it be the case that small Hamming distance assignments satisfy more clauses than a random assignment, than sort of the bulk of the assignments living out in space? And part of the reason is that in order to flip a clause from true to false, you need to flip exactly the set of variables that correspond to the literals currently set true. And you need to not flip any of the variables that correspond to literals currently set false. So this is pretty demanding. And for particular small example to sort of get a bit of an idea, imagine being Hamming distance 1 from this assignment A, which satisfies our formula phi, where A happens to be the assignment of everything set true for our convenience. So great, in phi, there's only 3 possible ways to flip a single variable to cause a clause to be false. And so despite the fact that phi should have something like 1/8 of its variables set false, by flipping literals at random, so for a random assignment, we're actually only getting 3/5 times 1/7 of the clauses set false, which is less. So we've, moved to a significantly lower range of clauses set false. And there's one misleading thing I'll highlight here that I've sort of done, which is I've implicitly acted like we know what the random assignment is. And in some sense, that's like if we picked a random assignment and then picked a random phi that happened to satisfy that assignment. But this, as it turns out, is not quite the same distribution as picking a random phi even then conditioning on phi being satisfiable and picking a random assignment that happens to satisfy phi. And I'll talk about this distinction a bit later. It turns out that these distributions at the threshold are close enough that it doesn't actually matter. And for many different algorithms and many different people's analyses, you can sort of overcome this difference, and we do as well. And I'll give sort of a quick and dirty proof for why you can overcome this. But just note that there is sort of a subtle difference between these two distributions. So next, let's talk about random assignments. So assignments that are far away from other satisfying assignments satisfy something like 1 minus 1 over 2 to the k fraction of clauses. We talked about this a bit earlier. To give sort of a crisp idea of what that means, out of all the clauses in our formulas at the threshold, this leaves the natural log of 2 times n clauses unsatisfied, roughly. So now, to like actually build some intuition, I'm going to show you the output of what you get if you actually just sample a random formula and check over all possible assignments, and then intentionally select, keep, selecting random formulas until you find one that has a satisfying assignment. And then over all assignments, you simply check how many clauses each assignment satisfies, and you build a histogram. And additionally, you pick a random satisfying assignment, and you consider all the small Hamming distance assignments around that satisfying assignment. And you also note how many of these satisfy different numbers of clauses. So that's what this picture is. The black bar is the threshold that we've talked about before, this threshold T, where we want to bother running our expensive, small Hamming distance search, this k to the alpha n search, on everything to the right of the assignment, to the right of the bar, and to the left of the assignment, we don't run anything. The small, in the red box, this small binomial looking distribution formed by the pink and green, that is the set of all the small Hamming distance assignments, the things that are actually close to the satisfying assignment, their distribution of number of satisfied clauses versus the number of assignments that hit that number of satisfied clauses. And this larger binomial, that sort of blue and yellow binomial, is over all assignments in total, how many assignments have different numbers of clauses they satisfy. And you'll notice that much like this intuition we sort of built earlier, that small Hamming distance assignments should satisfy more clauses than random samples. This is in fact true. And even better, these kind of look like binomials. And binomials tend to have pretty good concentration, and you can get some nice tail bounds. And that also happens to be true. This picture is for a very small k and a very small n and a very small m, because you don't want to exhaustively search over 2 to the n things for very large values. So here all the ratios don't look too impressive, but as you grow the number of variables you're talking about and the number of clauses correspondingly, you get quite intense concentration. You get sort of exponential fall off of how likely something is to be passing this threshold bar. So really what we're doing is abusing the fact that we have 2 different binomial distributions, and we throw a threshold bar between them, and we just ask, how often do you actually pass this threshold bar? So this intuition works, that there's something you can test to distinguish between small Hamming distance assignments and random looking assignments. And it's whether or not they pass this threshold T number of clauses that they satisfy. So once again, just to highlight, and with a blown up picture of our small value, why should this test work? It should work because it is really the case that small Hamming distance assignments satisfy more clauses, and in a way where we can throw up a threshold such that we don't do a lot of the work we would have otherwise had to do. So now what does this give us in terms of a running time for our algorithm? Well, we get an algorithm that runs in time 2 to the n times 1 minus log squared k over k. So we get like a whole nother factor of log k by just sort of paying attention to what assignments actually look like around a satisfying assignment, by sort of paying attention to the structure that we're getting from this random formula. I'm now going to move on to explaining where this number log squared actually comes from and how we get that. Hopefully, like, I'm hoping that everything so far has made sense. And so I'd like to pause, and if anything about the algorithm or the threshold or like why intuitively this should work doesn't make sense, please ask some questions now.
Do we know that this shouldn't work in the worst case? Say, do we know formulas where SAT assignments have most of their neighbors and satisfy very few clauses or something like this?
I think you can construct some where it's not super different from, like, I think you can construct things where the threshold we picked isn't right. I'm not sure if there's anything where you can actually make it indistinguishable from random. I think one of the bigger issues is less that small Hamming distance assignments don't look right, but that the random assignments don't necessarily look right. Like, there's nothing you can do to make the mean different, even on a worst case formula, but you don't need to have things look like a binomial, at least not necessarily. And I don't know how to, roughly the problem I ran into is I don't know how to prove that you don't have something with the correct mean, but sort of too many, nearly satisfied assignments with a bunch of like very unsatisfied assignments. I'll admit that a lot of the examples where sort of weird bad things happen look pretty silly. They're things like you repeat the same clause a bunch of times, or you have a really biased like you have a variable x appear way more times when it's true than when it's false, or other things where like you can look at this and be like, well, now I know what the satisfying assignment is because I like read it off of, like, I have no examples that don't have silly properties like that, but examples exist where these things break down, unfortunately. Yeah, I do sort of hope that you can take some of these ideas into the worst case. But yeah, so when analyzing our algorithm, I'm going to talk about primarily the true positive and false positive rate, but you can similarly have defined true negative and false negative. Where what I'm looking for here is there's this thing we'd like to know, but that we can't directly access without an expensive runtime, which is like whether or not something is a small Hamming distance away from a SAT assignment, so close to a SAT assignment. And a true positive is going to be something that it both is close, like we want, and passes our test, has more clauses it satisfies than the threshold. A false positive is going to be something that doesn't, like, is not close to a SAT assignment, but it passes the test, and so we run our expensive search anyway. And this is sort of our like wasted time measure. And it turns out you can sort of describe how fast our algorithm is entirely in terms of the probability of a true positive, which is the probability of sampling a true positive. So out of all 2 to the n assignments, how many of them are both within the small Hamming distance of the satisfying assignment and pass our test, and probability false positive, so how many things both are far from a satisfying assignment and fail to pass our test. So if you imagine you like have access to this for some particular formula phi, then the algorithm works as follows, right? We need to make enough samples. We need to like take enough random points that we actually find a true positive, given that there is a satisfying assignment. Additionally, we need to run our local search, this k to the alpha n search, both on one example where you're actually close to the satisfying assignment, that one true positive you found potentially. And additionally, you need to run on a bunch of things that are just wasting your time. All the times we've passed the test, but we shouldn't have. And we expect the number of these to be roughly the number of false positives, the probability that you hit a false positive over the total number of samples. So, multiplied by the total number of samples. So we get something of the form 1 over the true positive rate plus the false positive rate over the true positive rate plus 1 multiplied by this runtime. And we can rewrite this to simplify it out a bit. It turns out that like single running of k to the alpha n for our like one satisfying assignment, this is like much faster than the other terms for all reasonable choices of alpha in our setup. So we can ignore that term. And the reason that's going to happen is because we don't actually get the false positive rate down to something trivial. Roughly, that's only going to be a problem if that's only going to be sort of a leading important term. If the false positive rate is so low, you just expect only like a constant number of false positives, for example. We unfortunately do not expect only a constant number of false positives. Given that, minimizing this whole structure ends up really being about trying to have the false positive rate times k to the alpha n being up to polynomial factors, roughly 1, like some constant, you can think of it. And the reason for this is that it equalizes the two terms in this sum. And it turns out this is in fact like the best way to minimize this. It's not necessarily generically true, but it is true here. So our question, of course, becomes how can we bound these two values, right? We need to get a lower bound on the false positive rate and an upper bound on the true positive rate. Excuse me, let me flip this. We need to say like our false positive rate is at most something and our true positive rate is at least something, because we're dividing by the true positive rate and multiplying by the false positive rate. So it turns out we can bound the false positive rate by taking a random distribution and just across all possible samples, bounding the number of positives that occur on the test. So we bound the false positive rate by bounding the false positive plus true positive rates. And you do this roughly by abusing the fact that this will actually look like a binomial. Binomials have like really nice tail bounds, and we just like take a tail bound saying you're not going to be above this threshold t with more than probability something. And we'll talk about that a little bit more later, but it is just sort of you're taking a binomial tail bound. So the problem with the true positive rate is that if you imagine like taking a random formula, one, maybe it doesn't have a sat assignment. So like, okay, now take a random formula and condition on it being a satisfied random formula. And now like imagine an arbitrary choice or a random choice of a satisfying assignment. Like what does the rest of the formula look like with respect to this assignment? That's sort of what we'd like to know in order to analyze the small Hamming distance. And oh my God, that does not sound like an easy thing to think about. So instead, we're like, okay, that's really hard. It'd be much easier to instead imagine a random assignment and pick a random formula that happens to satisfy this assignment. But as discussed earlier, it's not exactly the same distribution. So we need to do two things. We need to prove that this planted distribution is actually close to the distribution we want, the random distribution. And secondly, we need to prove that our algorithm succeeds with high probability in this planted distribution. Luckily for us, the second thing is once again just a tail bound. So like really in some sense, this entire question of how we bound these values is that the tail bounds of binomials are great. And secondarily, the planted distribution is pretty close to the random distribution. That's the high level idea of the whole analysis. So, once again, if you take a random assignment and a random phi, the average number of clauses that you're going to satisfy is m over 2 to the k. In fact, if you take even a worst case formula and a random assignment, your average number of clauses you satisfy is this m over 2 to the k. You can't avoid it. But what we can do when we know that it's a random assignment and a random phi is we bound the tail of the distribution over all assignments, all random assignments and all random phi of how likely you are to be in this tail. And then we can bound the number of random phis that have way too many values in their tail. And so we can say with high probability, your random phi is not going to have too many values in its tail. So this is sort of the trick we pull. We like do things over a distribution on both random assignments and random phis, and then we say like, there aren't that many random phis that cause you to spend a bunch of like useless work. It turns out like when you run all of this and you get your values out, our false positive rate is this heinous equation. If you'd like to get an intuition of where this horrible heinous equation is coming from, notice that 1 minus alpha to the 2k and 1 minus alpha to the 4k are, 1 minus alpha to the 4k is the square of 1 minus alpha to the 2k. And that's actually where it's coming from. Like roughly your number of expected false assignments were decreasing by an entire factor of 1 minus alpha to the 2k. And it turns out that makes you 1 minus alpha to the 4k less likely in your mean, roughly, to happen. So phi with high probability isn't going to have more than a false positive rate of this 2 to the negative n times 1 minus alpha to the 4k divided by 32. Great. Next, we need to do the harder thing. So, once again, our true positive rate, we're going to work in the planted distribution. We're going to consider assignments that are Hamming distance alpha n from our satisfied value. And we'll show that our algorithm works with very high probability in the planted distribution, and then show that that means that it also works well in the random distribution. So first, let's like actually formally define the planted distribution. We're going to pick an assignment at random, a from 0, 1 to the n, and then we're going to pick each of the m clauses independently at random from all k-length clauses that happen to be satisfied by a. So this is almost the same distribution as our random distribution, except every time we like are picking literals, roughly, you can think of this as like we pick all the variables at random just the way we would before, and we pick k minus 1 of our literals totally at random just as we did before. But that last literal, if all previous k minus 1 of the literals have been set in such a way that the clause is currently set false, we now force that last one to be true, and then you scramble things so that you don't have the last one set. So you can think of this as a distribution. So it's like quite close to the random distribution, but we are like excluding 1 over 2 to the k of our possible literal settings from all clauses. So there's various previous work that shows that the planted distribution and random distributions are similar, especially at the threshold. So first, let's like, say, what happens, not worry about the planted distribution, but just worry about how likely we are to be satisfied given that we're at Hamming distance alpha n and we're in the planted distribution. And it turns out the average number of false clauses is going to be m times 1 minus 1 over alpha to the k divided by 2 to the k minus 1. And where this is coming from in the end is exactly the statement of like, you need to flip exactly the variables, like you need to flip for any given clause to be falsified, you need to flip exactly the literals in those clauses. You have a set of literals that are set false by your formula. You need to not flip those variables, and you have a set of literals set true. You must flip each of those, and that's how you end up getting this term, given that you're flipping alpha n of your literals. And if you compare this to our value of t, you'll notice that we've roughly taken, like, this average number of false clauses is roughly like the average number of false clauses for a random assignment, but multiplied by 1 minus alpha to the k. And we take this 1 minus alpha to the k and we square it to sort of split the difference between our random assignments and our Hamming distance assignments. So that's how we're like setting this threshold t. So the means of our two distributions are indeed different. And once again, because you can sort of think of this as like, I pick a random assignment, I pick some arbitrary choice of small Hamming distance assignment from that satisfying assignment, and then I pick, you know, random clauses in our formula. These are each independent events. We once again get a binomial, and once again we can sort of say like, okay, jointly across the randomness of the SAT assignment and the small Hamming distance assignment and the random formula, this is unlikely. And then you can ask like, okay, what percentage of formulas sort of have some unusual setup where they have way too many of their small Hamming distance assignments looking bad, and you can say that's quite unlikely. And so you can say like, all right, with high probability, your with like quite high probability, you in fact get over half of your small Hamming distance assignments passing this test, and that's what's proven. So now that we've like argued that in the planted distribution things look good, what happens when we're moving between planted and random? And first, let's sort of discuss why they're not quite the same thing. So in the planted distribution, we have a phi and an assignment that satisfies it, right? And in fact, we sort of generate the assignment and then generate the phi. Whereas in random Kcnfsat, we just have the phi. But notably, this means if a given formula has lots of satisfying assignments, it shows up a lot of times in this planted distribution. And this is in fact exactly what's sort of going wrong in saying that they're the same. In my like, you know, very simple, silly diagram over here, phi 1 has 2 satisfying assignments, whereas phi 2 has 1 satisfying assignment. And as a result, phi 1 sort of appears twice as often compared to phi 2 in the planted distribution. Now, in the extreme case, also, the planted distribution includes no formulas that have no satisfying assignments, whereas some of those exist for random formulas. Great. So what we're going to do in arguing that the relationship between the planted and random distributions isn't so bad is that we try and count the total size of the left bar. That is the total number of phi, comma, an assignment that satisfies the phi tuples. And this is just 2 to the n for all the possible assignments A. And then you need to pick m clauses. And these m clauses can be any choice of n variables, one after each other. Sorry, k variables, one after each other. And then we get k minus 2 to the k minus 1 possible settings of our, you know, falsifying or not falsifying the variable. And we put that to the m because we have m clauses. And you should compare this to the number of phis by themselves, which is just n to the k times 2 to the k to the m. So this is, you know, all possible choices of clauses. We get m of them. That's it. The ratio of these is 2 to the n times some constant divided by 2 to the k. So notably, this isn't exponential. These are like, you know, exponentially sort of different distributions, but that's a very small exponential. And so crucially, if something is very, very unlikely in the planted distribution, right? Like if it occurs 2 to the n, if it only occurs 1 over 2 to the n divided by k times, then it can occur at most in the random distribution, that multiplied by 2 to the n times some constant divided by 2 to the k. And crucially, like, you know, n minus 1 over k plus 1 over 2 to the k, like the 1 over 2 to the k term is like much, much smaller than this other term and is thus basically irrelevant. So anything that's like vanishingly unlikely in the planted distribution continues to be vanishingly unlikely in the random distribution, despite the fact that you in fact do get this exponential change in how likely it is. So this is sort of the funny thing, like we're dealing with exponentials, and so like we have a notion of small exponentials versus large exponentials. Great. So there's like a little sleight of hand I did here, which is that if all you want to say is that your algorithm succeeds with good probability over the random distribution, everything I just said is totally fine. You can ask potentially for something a bit stronger. You can say, I don't just want that. I want that my algorithm succeeds with high probability on formulas that are random, conditioned on them being satisfied. And I want to succeed with high probability on formulas that are random, conditioned on them being unsatisfied. So like I want my algorithm to like actually do both well. And if you want to say that, you need to additionally, you need to not just compare sort of the size of the bar of planted sat and the size of the bar of random sat, you need to compare the size of the bar of random sat conditioned on those formulas being satisfied. And that's potentially a smaller bar. And it turns out we can bound the probability that a random sat formula is satisfied, and then still get this like sort of same kind of property that anything that's vanishingly unlikely in the planted distribution continues to be vanishingly unlikely in the random distribution.
Andrea, but for this, you need to know the threshold for Kcnfsat?
Yes. Yeah.
So this would only currently work for large enough K?
Yes.
Okay.
Yeah. So actually, this is a good point. So this entire algorithm works for large K. We don't, in some sense, we don't like truly rely on the threshold existing so much as we rely on K being sufficiently large such that certain properties hold. But, you know, we do rely on a large K here. The one funny thing is the experiments where we like actually sample some random formula. We sampled formulas with small k because those are of course like much easier to check everything over. And those do actually look like they have all the nice binomial distributions we want and like everything seems to hold. So we don't know how to prove that that should be true for small k, but it does appear to be, as a matter of fact, true for small k. So whatever, it's one of those things that's like true, but we don't quite know how to prove it. Yeah, so like in the end, what we get is that, you know, with very high probability, our true positive rate for a given formula, given that it has any satisfying assignment to begin with, is going to be at least half of all the small Hamming distance assignments that existed in the first place. And what that means is that the true positive rate is going to be at least n choose alpha n, the size of the Hamming ball, over 2 to the n, you know, missing some constants. But like, what's a constant between friends when we're talking about very large exponentials? And yeah, so up to constants, which we don't really care about, this is in fact the best possible value of the true positive rate. So you can't sort of hope to potentially do better. So now we can bring this all back. Like, we want to know how fast our algorithm is and like figure out where we're getting this log squared value from. And in order to do this, we bounded the true positive rate and the false positive rate. And we, you know, got a bound on the true positive rate that's as good as we could possibly hope for. And I'm going to sort of, I'm realizing I'm now over time, so I'm going to like hand wave away some of this math. But it turns out if you set alpha to be something like log k over k, more specifically log k over 16k, we get this nice property we wanted of equalizing the two terms of our equation, so that our running time can in fact just be simplified to 1 over the true positive rate. So when we set alpha equal to something like log k over 16k, and we care about this 1 over the true positive rate, we plug in, and it means our runtime is 2 to the n over n choose alpha n. And this term just ends up being equal to 2 to the n times 1 minus log squared k over k. So what did we need in order to get all of this? Well, we needed a binomial tailbound for our false positive, a binomial tailbound and the equivalence of the planted distribution and random distribution at the threshold. And finally, we needed that the means of these distributions actually look different, right? Like these binomial tailbounds only help us if the means are sort of substantially different from each other. And what this gives us is this faster algorithm. So I promised something about the SAT clauses. Basically, if you have a naive test that just goes clause by clause and produces a score, and then you sum over all these scores, you can't actually do better than, you can potentially get a better constant in your like log squared k over k, but you're not going to be able to get a better function than log squared k over k, even if you come up with a more clever test. Whatever test you come up with, better be comparing large numbers of clauses or doing something across the whole formula. So the conclusion, we get this faster algorithm. Our our framework has the potential to do quite a bit in terms of getting faster if you come up with a better test. Though, as we said, the naive test doesn't work better. Future work involves, of course, getting faster algorithms, whether it's with this framework or some other framework. But also crucially, a fine-grained worst case to average case reduction would allow us to transfer some of these findings we have at the threshold to better algorithms in the worst case, which would be great. We love worst case algorithms. So a reminder, sample and test algorithm. We're sampling things, checking whether or not it passes our test, and then searching locally only around those points. Any questions?